In this video, I would like to make a couple of simple points about parameters. The general shape of the distribution is given in a mathematical form in which certain constants or parameters are left unspecified. If you look at the upper left of your screen, in the case of the exponential function, that constant is beta. Once we know what beta is, once beta is specified, then the probability distribution, and consequently the probability of any event, is completely determined. This is a considerable achievement to arrive at the conclusion that the probability distribution of a random variable has a certain parametric form. When we find that parametric form, not only is the number of possible distributions that we must consider greatly reduced, but insights beyond the range of our past experience, that is, beyond the range of the observable data that we have, are obtainable through extrapolation and interpolation. And this is a powerful tool for a risk assessor. Elsewhere in our course, we will have spoken about parametric and non-parametric distributions. I'd like to build on this point that I just made here to make another point about parametric and non-parametric distributions. So take a look at this page. On it you find the density function and the cumulative distribution function for four distributions. The density function is given by this f of x, and the cumulative distribution given by this capital F of x. On the top left is the function for the triangle distribution. To its right is the formula for the uniform distribution. And here's what I want you to see. There are no parameters in these functions. That is, there is no constant left unspecified. These distributions are entirely defined by your data. The minimum is the smallest data point. The maximum is the largest data point. These values are likely to change depending on who's estimating them. So in this sense, they are not constants of nature or unassailable truths. So in this function here and this function here, there are no numerical parameters that are constants that we must specify. By comparison, beneath them you find two examples of parametric functions. On the lower left, the one we're looking at now, is the function for the normal distribution. Notice that in addition to the variable values, the x values here, and this defined constant e, there are two unspecified parameters, mu and sigma, the mean and standard deviation respectively. To use this distribution, you must have enough data to specify the value of these two parameters. To the right is the formula for the Weibull function. It too has two parameters. Some parameters many of us have encountered before. The mean and standard deviation are two examples. Others, like the alpha and beta for the Weibull, are not at all familiar or intuitive. In general, all other things equal, risk assessors prefer distributions with fewer parameters than distributions with more parameters. And that's simply because it's easier to get one good estimate than it is to get two or three or four or even more estimates. So when you look at probability distributions, if you dig into the math, and we won't do that too often, but if you were to dig into the math like we did here, look at the density functions and the cumulative distribution functions, you would find that some have these numerical characteristics or parameters. They would be parametric distributions. Other distributions are defined simply by the data. These are non-parametric distributions.